Welcome you all for the class of Discrete Mathematical Structures. 18 CSC 36 is the subject code. I'll be teaching a topic in Module 1, Fundamentals of Logic. Topic name is Laws of Logic. Myself, Dr. Madhura, Assistant Professor, Department of Mathematics, Sai Vidya Institute of Technology, Bengaluru. Laws of Logic. Let T naught denote tautology and F naught denote the contradiction, and P, Q, R be the propositions, then the following laws hold. We are assuming T naught to be the tautology and F naught as the contradiction, and we have P, Q, R as the propositions. Then the following laws holds good. First one, commutative laws. P or Q is logically equivalent to Q or P. Second one, P and Q is logically equivalent to Q and P. These are our commutative laws, one with the or, other one with the and connective. Next we have associative laws given by P or Q or R is logically equivalent to P or Q or R. It is just the brackets variation, and you observe that both are or, and here also both are or in the right hand part. Similarly with the and, we can write down P and Q and R is logically equivalent to P and Q and R. So associative laws are just the bracket differences. As and when required, we can just interchange in this manner and write down the expression. Distributive laws. P or Q and R is logically equivalent to P or Q and P or R. We observe it is a combination of both or and. There is a or symbol and the and symbol. And we write down the distributive law by distributing the expression. That is, we write it down as P or Q first. And there is an and symbol, write down the and outside. Then we have P or R. Similarly, we can have another distribution law with the and outside and or inside. So P and Q or R is logically equivalent to P and Q or P and R. So distributive law is a combination of both and or. Next we have De Morgan's law. First one, negation of P or Q is logically equivalent to negation P and negation Q. Negation of P or Q when you want to take negation for both of them, the symbol becomes and. Similarly, the vice versa of this, that is negation of P and Q if you have, this is logically equivalent to negation P or negation Q. Next we have law of double negation, that is negation of negation P is logically equivalent to P. Double negation, law of double negation. So negation of negation P is logically equivalent to just P. Next we have idempotent laws. Idempotent laws, first one says P or P is logically equivalent to P itself. So when you have any expression of the form P or P, then it is equivalent to writing just P. Next we have P and P. P and P is also logically equivalent to writing just P. These are idempotent laws. Next one, identity laws. P or F naught is logically equivalent to P itself. F naught is nothing but contradiction. So if you have P or F naught, we will be getting back P itself. This is similar to understanding that F naught is nothing but the contradiction. So contradiction takes truth value 0. So if you have P or 0, then P itself. Similarly, P and T naught. T naught is nothing but the tautology which takes the truth value 1. So when you have P and 1, you'll get back P itself. Next, inverse laws. First one of the inverse law is P or negation P is logically equivalent to T naught. T naught is nothing but having the truth value 1. So P or negation P. This also you can give the any truth value for P and check out it is always equal to 1 itself. Suppose P is 1, 1 or negation P means 0. So 1 or 0 gives us 1 itself. So that is the reason P or negation P is logically equivalent to T naught. Similarly, P and negation P is logically equivalent to F naught. P, if I take 1 as a truth value, P and 0, negation P will be 0. So 1 and 0 will give us 0 always. So that is the reason this is logically equivalent to F naught. So these two are inverse laws for us. Next we have domination laws. In that first one, P or T naught is logically equivalent to T naught. And the second one is P and F naught is logically equivalent to F naught. So suppose you again take the truth value for P as 0. So 0 or 1. T naught is nothing but having the truth value 1 always, which represents the tautology. So 1, if you take P as 0, 0 or 1 gives you 1 itself. If you take P as 0, 0 or 1 again gives you 1 itself. So that is why P or T naught is logically equivalent to T naught only. Similarly, P and F naught is logically equivalent to F naught. You can give any value of P and check the truth value. This will be always 0. These are your domination laws. Next we have absorption laws. P or P and Q is logically equivalent to P itself. We have a combination of or and we observe that one of the proposition is repeated. So P is repeated, so we get back P itself. This is absorbing Q. So that is why absorption law. So P or P and Q is logically equivalent to P. Similarly, P and P or Q is also logically equivalent to P itself. That which is repeated comes back. So these are your 10 laws for laws of logic. We have to memorize all these laws when we have to do the problems. Remark: negation of P or Q is logically equivalent to negation P and negation Q. It's an application of De Morgan's law. And this is also the same. Negation of P and Q is logically equivalent to negation P or negation Q. Third one we have negation of P conditional Q. Negation of P conditional Q is always logically equivalent to P and negation Q, or P conditional Q is always equivalent to negation P or Q. So these also we need to memorize along with the 10 laws. The fourth one, either the fourth one or the third one we memorize, which will help us to do the problems. So suppose I have P conditional Q. This is always equivalent to writing negation P or Q. If you want, you can write down the truth values of P and Q and verify the resultant on the left hand side is always logically equivalent to the resultant on the right hand part. Next we have the definition for dual. Suppose S is a statement. If S contains no logical connectives other than and or, then the dual of S, usually denoted by S suffix D, is the statement obtained from S by replacing each occurrence of and or by or and respectively, and the occurrence of F naught and T naught is replaced by T naught and F naught respectively. So suppose a statement is given which I am denoting by S, and this has no other logical connective suppose other than and or. So only and or are involved in the statement S for us. Then we want to write down the dual of S means, which is denoted by SD. The dual can be obtained, dual of the statement S can be obtained by replacing and or by or and. So wherever and is there, replace that by or, and wherever or is there, replace that by and in the statement S. And suppose in the statement S we have F naught and T naught, replace both F naught and T naught by respectively T naught and F naught to obtain the dual of the given statement S. Say for example, suppose S is a statement P and negation P or R and T naught. Then the dual of this statement can be written as P or negation P. You observe and is replaced by or here. So P or negation P. Then we have or outside which is replaced by and. R and T naught. And is again replaced by R. T naught is replaced by F naught. So every occurrence of and or is replaced by or and respectively, and every occurrence of F naught and T naught are replaced by T naught and F naught respectively. So that's how we obtain the dual of a particular statement. A remark: if P is any primitive statement, then we can write down dual of the primitive statement whole dual is logically equivalent to P itself. That is nothing but dual of P is logically equivalent to P only. Twice when we take the dual of a statement, it is logically equivalent to dual of the, it is logically equivalent to statement itself. Second one, if P is logically equivalent to Q, then dual of P is logically equivalent to dual of Q, which is nothing but the principle of duality. Suppose a statement says that P is logically equivalent to another proposition Q, then the dual of P is logically equivalent to dual of Q. This is nothing but the principle of duality. So this is all about the theory part in laws of logic. So we'll be working problems on laws of logic. This is without truth tables. We'll see problems on laws of logic. Problems on laws of logic. First question. Prove the following logical equivalence. Prove the following logical equivalence without using truth table. Without using truth tables, or it can be also given as using laws of logic. Using laws of logic. First question. P conditional Q conditional R is logically equivalent to P and Q conditional R. Second one, negation P or negation Q conditional P and Q and R. This whole thing is logically equivalent to P and Q. Third one, P or Q or negation P and negation Q and R. This entire expression is logically equivalent to P or Q or R. Fourth one, P conditional Q and negation Q and R or negation Q is logically equivalent to negation of Q or P. And fifth one, negation P and negation Q and R. This whole thing, or Q and R or P and R is logically equivalent to R. Solution. First one, we have to prove that P conditional Q conditional R is logically equivalent to P and Q conditional R. So we'll consider the LHS part of it and prove the or arrive at the RHS using the laws of logic. So consider the left hand side, that is P conditional Q conditional R. P conditional Q conditional R, this is logically equivalent to, writing down three parallel lines is also another notation for logical equivalence. Hope you remember that. So P conditional Q conditional R is logically equivalent to P conditional Q conditional R can be written as negation Q or R. This is using the property that we have used a property here. So let me write down which property we have used it here. This is because P conditional Q is logically equivalent to negation P or Q. P conditional Q is logically equivalent to negation P or Q. This was a remark what we learned in the theory part, right? So we have used this and obtained the expression for Q conditional R as negation Q or R. Negation Q or R. Now again, moving ahead, again this is of the form P conditional Q. P conditional Q form. So we can write down again in the form negation P or Q. So this is equivalent to negation P or, in place of Q we have negation Q or R. Negation Q or R. Now both these are or and or, no? Both these notations are or. So we can just use associative law and group the terms. So this is equivalent to negation P or negation Q or R. Negation P or negation Q or R. So here I have applied associative law. Associative law. Next, this in turn can be written using De Morgan's law as, using De Morgan's law, we can write it down as negation of P and Q or R as it is. So here we have now applied which property? We have applied De Morgan's law. De Morgan's law. Correct? Now what is our requirement? Always looking into the requirement also we need to proceed further, right? So our requirement to the right hand part is P and Q conditional are. So again I want to put it in the form of conditional. So I already have the expression in the form negation P or Q. Correct? Looking into the arrows, negation P or Q form we have. We can write that down as P conditional Q. Negation P or Q is logically equivalent to P conditional Q. So we can write it down as P conditional Q form. So this negation goes off. So this is logically equivalent to P and Q conditional R. Conditional R. So we have all actually applied the property once again. The form that this was of the form negation P or Q form, which is logically equivalent to P conditional Q. P conditional Q. So we applied the reverse way of this property, that's all. So it was already of the form negation P or Q. We applied and wrote it of the form P conditional Q. Right? So this is how we work out problems without using truth tables or using the laws of logic. We need to obtain the resultants, whatever is being given for all the 5 of them. So this was the solution for the first one. Now we will prove the second one. Second one is to prove negation P or negation Q conditional P and Q and R is logically equivalent to P and Q. So this is our second thing what we have to prove. Let us consider the left hand part and prove the right hand side of it. So second one. Consider the left hand side, that is negation P or negation Q conditional P and Q and R. P and Q and R. So this is logically equivalent to, we'll first remove the conditional form. So I assume the first bracket as say P conditional Q. It is of that form. So what is P conditional Q? P conditional Q is always logically equivalent to negation P or Q. Negation P or Q. So I will apply negation P. So negation P or negation Q. Negation P or Q. In place of Q I have P and Q and R. P and Q and R. So here we have applied which property? I will just write down that property for you. So we have using P conditional Q is logically equivalent to negation P or Q form. So using this we have obtained that expression, right? Now here we have observed in the first bracket I have negation P or negation Q. I will apply De Morgan's law and take out this negation so that I can equivalently, this is logically equivalent to, so negation I already have. Now applying De Morgan's law, I will get negation of P and Q, negation of P and Q, and remaining I will write down as it is, or P and Q and R, or of P and Q and R. I have written the remaining part as it is. This is application of De Morgan's law. Correct? I'll just write down the reason here. So how did we get this is using De Morgan's law. It is always preferable to write down along with the reason which law you have applied and got the expression, so that there is a better clarity also. Correct? So preferably write down which law you are applying. Now what is this negation of P and Q? Law of double negation. So we just remain with P and Q or P and Q and R. So here we have now applied law of double negation. Law of double negation. Law of double negation we have applied and we have got this. Next step, what can we do in the next step? See, I observe I have here P and Q. Here also I have P and Q and R also. So I'll just use bracket for P and Q, applying the associative law. So this is logically equivalent to P and Q, or P and Q, I will put a bracket, and R, and R. So this is an application of associative law. Associative law. Next, what did they help me applying the associative law? It helped me to observe an expression here, correct? I will just show you by underlining the expression. See, observe, this is of the form, I assume this as say P, okay, say capital P for just understanding purpose. Then here also I have the same expression, no, P and Q, so that is nothing but P itself and Q. It is of this form, P or P and Q. What is P or P and Q? This is logically equivalent to P itself. It is an application of absorption law. So it is of the form P, or P and Q I am assuming as just capital P, and R I am assuming as capital Q. So it is of the form P or P and Q. This is logically equivalent to P by absorption law. So one will be and, the other one will be or, and what is repeated comes back, Q get absorbed. So that is nothing but the absorption law for us. So what comes back is P and Q. What comes back now is P and Q. Correct? So I will just write down this is logically equivalent to P and Q. That is our requirement if you observe. And before that, let me quote the reason. This is because of absorption law. Due to absorption law. So have we arrived at the requirement now? Our requirement just we will look into. It was like this. Negation P or negation Q conditional P and Q and R is logically equivalent to P and Q. Yes, we have proved it. It is logically equivalent to P and Q. So this was the solution for the second one. Now we will move on to third one. Third one, I consider the left hand side of the third one and prove that it is logically equivalent to the right hand part. So it is P or Q or negation P and negation Q and R. Right? So I have to take P or Q or negation P and negation Q and R, and I have to prove this is logically equivalent to P or Q or R. Okay? So let me consider the left hand part of it. So what is it? P or Q, P or Q, or negation P and negation Q and R. Okay, this is my left hand part. I have to prove this is logically equivalent to P or Q or R. Right now? So first, observing this small bracket down, I will put a bracket and write it down applying the associative law. I mean to say, this can be equivalent to, logically equivalent to P or Q, correct? For convenient, we can put a bracket here because this was separately given for us. So P or Q, or I can group these two terms together, no, negation P and negation Q together, and R I can write down separately. Correct? This is an application of associative law for us. Application of associative law. Associative law. Now this in turn is logically equivalent to, using De Morgan's law, I can write down negation P and negation Q can be written as negation of P or Q. Negation of P or Q that can be written. So this is logically equivalent to P or Q, or P or Q, or this is negation of P or Q, negation of P or Q, and R as it is. Correct? I'll just repeat it. First I will write the reason. So this is application of De Morgan's law. De Morgan's law for us. Right. So what did I actually do? I applied negation P and negation Q can be written as negation of P or Q. Application of De Morgan's law for us. The rest all expressions I have retained as it is if you observe. Correct? Now, what is the next step then? Next step, I can observe here that I can apply distributive law here. P or Q or negation of P or Q and P or Q or R, which is an application of distributive law for us, right? So this is logically equivalent to P or Q, P or Q or negation of P or Q. This is one expression for us, and P or Q or R, P or Q or R. So this is an application of distributive law. So recall distributive law once. Distributive law says that if you have P or negation P and Q, it is of that form. P or negation P, P or P and Q you can say. P or P and Q can be written as P or Q and R can be written as P or Q and P or R. So applying distributive law, we have got it. Correct, no? Next. This is logically equivalent to, observe the first bracket term. It is an application of inverse law. So what is inverse law for us? Suppose I have P or negation P. P or negation P is logically equivalent to T naught. P or negation P is logically equivalent to T naught. So application of inverse law for us. So this is logically equivalent to T naught and P or Q or R. T naught and P or Q or R. So I'll just write on the law here. We have applied inverse law. Inverse law. Next. Applying commutative law, this can also be written as P or Q or R and T naught. I applied commutative law for convenience because the next step is application of another law. So this is commutative law for us. Commutative law for us. And finally, applying the identity law, we can write it down as P or Q or R. P or Q or R. This is using identity law. So we'll recall what is identity law. Also. So this is an application of identity law. Okay. So what is identity law? I'll just recall it for you. P or P and T naught. We have two identity laws, no? One is with respect to T naught, the other one is with respect to F naught. So if I have P and T naught, it is logically equivalent to P itself. So this is bracket, this bracket I am assuming as P and T naught is logically equivalent to P itself. And that's an application of identity law for us. So have we proved the required thing? We had to arrive at P or Q or R only, no? P or Q or R only. Third one, right? So one more observation here. While writing the second term here, I should have written a P or Q bracket, but that is obvious. I avoided it because it's an application of associative law. If you want, you can write down a bracket here for P or Q and later remove the bracket and write down the law name as associative law. Okay, that doing it or avoiding it, both are okay. So it arrives at the required resultant for us. So this was the third sub question for us. We'll prove the fourth resultant now. Fourth one, P conditional Q and negation Q and RR negation Q is logically equivalent to negation of Q or P. We have to prove this logical equivalence using laws of logic now. So fourth one I will write down. Fourth one, I'll take the left hand part of it. So this is nothing but P conditional Q and negation Q and R negation Q. This is logically equivalent to, I'll write on below itself, this is logically equivalent to. So firstly, we will use P conditional Q expression. We have to remove the conditional always, okay? So P conditional Q is logically equivalent to negation P or Q. So we'll write on that first. So negation P or Q, the rest all I will write on as it is, and negation Q and R or negation Q. So here which expression, this was a remark what we learnt in the theory, correct? This is an application of, I have used P conditional Q is logically equivalent to negation P or Q, right? This expression I have used and obtained the result, right? Next, so next we will apply commutative law, negation Q or R. We will write down R or negation Q as negation Q or R and applying the commutative law. Okay, so this is logically equivalent to negation P or Q and negation Q or R. So I have just changed this part. R or negation Q is written as negation Q or R. This is an application of commutative law. I'll write down here commutative law. Right. So in the next step, what is the help of what is the use of writing down that commutative law is? Here now I can absorption law. I can apply absorption law here now. P and P or Q. It is of that form. Negation Q is repeated. So P and P or Q is logically equivalent to P itself, which is an application of absorption law. So I am applying that absorption law now. Negation P or Q and I just have negation Q here. Correct? So this was an application of absorption law. Recall absorption law. P and P or R is equivalent to P itself. So this is absorption law. Next, we can now observe these expressions negation P or Q and negation Q. We'll apply distributive law. One is or, the other one is and, no? So we can apply distributive law. This is equivalent to negation P and negation Q or Q and negation Q. Q and negation Q. So this was an application of distributive law for us. Distributive law. Next, we have two different laws applying for two different brackets, correct? No, one by one I will do. First term I will apply De Morgan's law for the first bracket. So this is logically equivalent to negation of P or Q. I will write down remaining as it is, or Q and negation Q as it is. Q and negation Q. So what did we do in the first bracket? We applied De Morgan's law. Next, for the second bracket, it is Q and negation Q. Observe Q and negation Q is nothing but F naught. It is inverse law. It is inverse law. So negation of P or Q, or this is nothing but F naught. F naught. Q and negation Q is F naught by applying inverse law. Inverse law. Next. Now we have this as P. It is just P I can observe, no? P or F naught. Using identity law, P or F naught is nothing but P itself. P itself. Here P is nothing but negation of P or Q. I am taking this entire expression as say capital P or F naught. Capital P or F naught is nothing but P only. It's an application of which law? Yes, identity law. Identity law. Right? Now one last law we have to apply. Our requirement is negation of Q or P. But here I have negation of P or Q. So I can apply commutative law and get the one last step. Correct? So this is equivalent to writing negation of Q or P. And this is an application of commutative law for us. Commutative law. So this was our fourth part of the problem. Now we will move on to the fifth one. Let's see what is to be proved. Negation P and negation Q and R, or Q and R or P and R is logically equivalent to just R. Correct? So in order to prove this, I will consider this first bracket, big bracket term separately and second bracket term separately, then apply OR between them. Okay, I felt that is convenient to do. So just for convenience, I'll be taking this expression and working on it separately, and the second expression working on it separately, then combining with the OR. Okay, so we'll just consider that one by one. Okay, fifth one. So first I will consider negation P and negation Q and R. Okay, I'm just considering this expression, which was one of the big bracket for us in the fifth part. This is logically equivalent to negation P and negation Q and R. I have applied associative law here. Correct? No, I have applied associative law and I have obtained this associative law. Right. Now next step, how can I write down the next step? Applying De Morgan's law for this bracket, I can apply, no? So this is negation of P or Q and R. Negation of P or Q and R. So which is an application of De Morgan's law for us. De Morgan's law. Right. Next, applying commutative law, I will rewrite this expression as R and negation of P or Q. Right? This is just for convenient. I'll be in requirement of that expression, so that is the reason I'm just taking it in that form of it. So this is logically equivalent to R and negation of P or Q. Negation of P or Q. So this is an application of commutative law for us. Commutative law. Right. Now we will consider another expression which was in the second bracket for us. I'll just show you that. So in the second bracket I had Q and R or P and R. So I will consider that and simplify that expression. So consider Q and R or P and R. This is logically equivalent to writing down as applying commutative law in both the brackets. Can I write it down as R and Q or R and P? We can write right. So we have applied commutative law for both the brackets. This is an application of commutative law for us. Commutative law. Application of commutative law for us. Now we can write this is equivalent to applying distributive law, correct? Applying distributive law, I can rewrite this expression as R and Q or P. R and Q or P, or in the next step I can rewrite this as R and P or Q. So here in the first step I applied distributive law, R and, here also I had R and, so I took that R and common kind of, then we remained with Q or P. So this was an application of distributive law for us. Okay, this was distributive law. Next step, we have written Q or P as P or Q, which is an application of commutative law. Commutative law. Right. Now you observe these expressions. Here also we arrived at P or Q form. Here also I arrived at P or Q form. And that was the reason here applying commutative law, and here also Q or P was written as P or Q just by applying commutative law for convenient. So that now I will be considering the required expression for us. So what is our required expression? There is an OR between these two brackets. So we consider OR between these two brackets and try to simplify the things what we obtained just now. Okay, so I'll just do it in the next page for you. So we have to take OR between these two brackets and simplify the expression. Correct, no? So therefore, I can write it down as negation P and negation Q and R. This was one bracket term, or Q and R or P and R. This was another bracket term for us. Now this is logically equivalent to, so what did we obtain for the first bracket? R and negation of P or Q. I write on the same thing, R and negation of P or Q I obtained. Correct, no? R and negation of P or Q. Correct. This is one separate expression for this. Okay, there is an OR between these two. So OR of what? R and P or Q. R and P or Q. That was a second bracket expression what we arrived at, R and P or Q. Now there is an OR between these two and we observe R and. Correct, no? So can I apply distributive law and combine these results? Yes, we can apply distributive law and combine these results. So this is logically equivalent to R and negation of P or Q or P or Q. P or Q. So this was an application of distributive law for us. Application of distributive law. So what will be the next step then? Next step, I can write down inverse law. Apply inverse law. This is of the form P or negation P. So if I assume this as capital P, P or Q as capital P, or this is of the form negation capital P. So P or negation P is nothing but T naught, applying inverse law. So this is logically equivalent to writing R and T naught. R and T naught. So which law did I apply here? I applied inverse law. Now what is R and T naught finally? R and T naught is nothing but R itself using identity law. Using identity law, this can be just written as R itself. R and T naught is of the form P and T naught. So this is logically equivalent to simply R using identity law. So this is how we work problems on using laws of logics and all. We had 10 laws. So using all the laws, we'll have to arrive at the required resultant. Next, second problem. Second problem I would like to take upon dual. Write down the duals of the following propositions. Write down the duals of the following propositions. We have to write down the duals of the following propositions. First one, P and Q or negation P or Q and negation R or S or R and S. Write down the brackets relevantly, properly. Second one, P or T naught and Q or F naught or R and S and T naught. R and S and T naught. Third one, P conditional Q, conditional R. Fourth one, P conditional of Q conditional R. So we have to find out the duals of the following propositions. So if you observe, the first and the second subpart of the problem can be directly written because it is fully with and or notations and F naught T naught. So recall the definition for dual. Dual of a proposition can be written as every and or are replaced by or and every F naught and T naught are replaced by T naught and F naught respectively. So first two are fully with the logical connective and ors. So we can just replace every and by or by and. Similarly, every T naught and F naught shall be replaced by F naught and T naught. First two are direct problems. Whereas the third and the fourth one, you have to remove the implication symbol. That is conditional symbol we have to remove and do. Right? So we have to use the property of P conditional Q. P conditional Q is always logically equivalent to negation P or Q. So using that condition, we have to remove the conditional symbol and we have to obtain the dual of this proposition also. Okay, so let's do one by one. Solution. So I'll be writing the dual of 1 and 2 directly. Dual of 1 and 2. I'll be directly writing it. So for the first one, dual is P or Q and negation P and Q or negation R and S and R or S. Wherever and is there, replace and by or, and wherever or is there, replace or by and. You'll get the dual of that expression. This was first one. Second one, replace T naught by F naught and F naught by T naught also. So we have P and F naught or Q and T naught and R or S or F naught. So you observe every or is replaced by and every and is replaced by or, and every F naught and is replaced by T naught and every T naught is replaced by F naught. So that's how we write on the dual of a proposition. This was for the first two. Now for the third one, we have to first simplify this P conditional Q conditional R. So I will consider that and simplify first. Third one, P conditional Q conditional R is logically equivalent to, for this P conditional Q I am applying the property first. So this is logically equivalent to negation P or Q. Negation P or Q, you can write on small p only everywhere. Negation P or Q. Then I have conditional R as it is. Conditional R I have written as it is. So again I have to remove that conditional also. So this will be logically equivalent to negation P or Q or R. Negation P or Q or R. Right? Now this in turn is logically equivalent to writing. So here both these cases, if you want, I'll write down which property we have used here. So in both of these we applied P conditional Q is logically equivalent to negation P or Q. So we applied this property and obtained the result. Correct? So next step, how can we write down the next step now? Using De Morgan's law, I can apply this. Negation P or Q can be written as P and negation Q. P and negation Q. I'll put a bracket for this, or R as it is. Or R as it is. Using De Morgan's law. We obtained this using De Morgan's law. Right. So now we observe that we just have the expressions which are having and or. And or only is contained. So now I can obtain the dual of this given proposition. So therefore, P conditional Q conditional R, the whole dual is nothing but P and negation Q or R, the whole dual. So now we write on the dual of this. So what is the dual? Replace every and by or and or by and. So we have P or negation Q and R. P or negation Q and R as the result for dual of the given proposition. Correct? So next we will do the fourth part of the problem. Fourth one and the last one of the problem. So it is of P conditional, Q conditional R is given. Again we apply the property P conditional Q is logically equivalent to negation P or Q. Negation P or Q. So I can write it down as negation P or Q is Q conditional R. And this in turn is logically equivalent to negation P or negation Q or R. So twice we have applied that property. Which property did we apply? P conditional Q is logically equivalent to negation P or Q. Negation P or Q. So both the cases we applied this property and we have got this expression as negation P or negation Q or R. Correct now? So again I can group the terms together, both are R. So applying the associative property, how can I write it down? So this is equivalent to negation P or negation Q or R. So I just change the brackets here using associative property, associative law. Using associative law we obtained this. Correct? So next we can now rewrite this expression as, using De Morgan's law, I can rewrite this as negation of P and Q or R. Negation of, correct no? Negation of P and Q or R, which is an application of De Morgan's law. This is an application of De Morgan's law. So if you observe here, now we have arrived at all and or only. So I can write down the dual of this expression now. So let us write down the dual of this expression. So therefore, P conditional, Q conditional R, the whole dual is nothing but negation of P and Q or R, the whole dual, and this is nothing but will be the answer for this then, negation of P or Q and R. Negation of P or Q. Every and is replaced by or and every or is replaced by and. Correct? So this is how we work problem on dual of the preposition. We'll see the next problem, third one. Verify the principle of duality. Verify the principle of duality for negation of P and Q conditional negation P or Q. The whole thing is logically equivalent to negation P or Q. So we have to apply the principle of duality and prove that if U, this entire left hand bracket part, we will understand it as say U. If suppose U is logically equivalent to V, if U is logically equivalent to P, then V, then we have to prove that U dual is logically equivalent to V dual. That proves the principle of duality for us. Okay, so before starting with that, so we will write down that given logical equivalence is of the form U is logically equivalent to V. Given is of the form U is logically equivalent to V, where U is nothing but, what do we have in place of U? Negation of P and Q conditional, negation P or Q, and what do we have in place of V? V is nothing but negation P or Q. So we have to find out U dual and V dual and show that they are logically equivalent to each other. Finding V dual is very easy because we don't have to simplify anything here. It just has OR symbol. So we'll find out V dual and keep it as equation 1, expression number 1. Okay. So therefore, V dual is nothing but negation P and Q. Negation P and Q. So I'll just call this as expression 1 for convenient. Now we consider this U and try to remove the conditional symbol and apply the U dual for the same. Okay. So consider U which is given by negation of P and Q conditional negation P or Q. We have to remove the conditional before finding the dual of U. So to remove conditional, we use the property P conditional Q is equivalent to which property? I'll just write down here. So I will be applying the property P conditional Q. P conditional Q. So this is logically equivalent to negation P or Q. So we will apply this property and obtain the expression for U. So U can be rewritten as negation of P and Q or negation P or Q. Right? So this was our expression for P. P conditional Q form it was there. The logical equivalence form is negation P or Q. So negation P means already a negation is there. So I have to write double negation of P and Q, or removing the implication symbol, we are writing or, that is what it says. Then the Q term I have written as it is. Q term I have written as it is. Okay, no? Now, negation of negation. Negation of negation, double negation. So I just remain with P and Q here. So this is P and Q, P and Q, or negation P or negation P or Q. So here we applied law of double negation. We just applied law of double negation and we obtained this expression. Okay, so this is and. Now we will find out the dual of this. Dual. So U dual is nothing but, we will write down U dual. So therefore U dual is equal to, is logically equivalent to, every and is replaced by or and every or is replaced by and to obtain the dual. So P or Q and negation P and negation P and Q. I just wrote the dual of the expression. Now, we apply idempotent law, correct? Before applying idempotent law, I can just group these two together by associative law, no? By associative law, I can just group these two together. So this is P or Q and negation P and negation P together I will write on. Negation P and negation P together I will write on. And Q separately. Okay, this is an application of associative law for us. Then this will help us to apply idempotent law and write it down as negation P and Q only. Right? So I'll just explain the same thing once again to you. So this was just changing the brackets. So negation P and negation P, I took it in one bracket and Q separately, and I applied associative law here. Associative law, and the next step I applied idempotent law. Let me recall what is idempotent law for you. Idempotent law says that if I have P and P, it implies P only. So P and P is logically equivalent to P only. So I had negation P and negation P, which in turn is just negation P. And Q I have written as it is. Okay, now, so this is idempotent law for us. Next we apply distributive law and write down this expression, right? So I have P or Q and negation P and Q, no? So I apply distributive law for this. So it is P and this bracket or Q and the second bracket. So that's an application of distributive law in the next step for us. P and negation P and Q, or Q and negation P and Q. This is distributive law for us. Distributive law. Next we can apply inverse law, or first we can apply associative law and group the terms, no? First we will group the terms by applying associative law. Okay, no? So I'll just apply associative law, so which is nothing but P and negation P first and Q, or here also I can just apply commutative law and write down Q and negation P. So in the first bracket, I used associative law by changing the brackets. In the second one, I just interchanged this negation P and Q as Q and negation P by applying commutative law. So two laws together I applied. I'll just mention the same thing to you. Associative and commutative law. associative and commutative law I applied. Two laws at a time I applied and showed it to you. Okay. So this is now P and negation P. So what is P and negation P? P and negation P is nothing but F naught using inverse law. Using inverse law, P and negation P is nothing but F naught, and Q I will write on as it is, or the second expression I have Q and negation P. Q and Q and. So it is nothing but grouping together Q and Q. I can write it down. Q and Q will just give me Q itself. So I have Q and negation P. Okay. So this is an application of inverse law for us. Inverse law for first bracket I applied no. So that I have written here. Okay. It's an application of inverse law for us. So what was the first bracket? Here we had F naught and Q, okay, or Q and negation P. Q and negation P for us. So this was logical equivalence. Applying inverse law. I just repeat this step once again for your convenience. So P and negation P is nothing but F naught using inverse law, and Q I have retained as it is. Here in the second bracket, we actually have Q and Q. By applying associative law, I can group these two terms together. So I will have Q and Q. Q and Q is nothing but Q itself using idempotent law. Q and Q is logically equivalent to Q only using idempotent law. So Q and negation P as it is. Okay, no? So now applying the domination law, I can write down F naught and Q as just F naught. F naught and Q is nothing but just F naught for us. F naught and Q is nothing but F naught for us, or Q and negation P I will write on as it is. Q and negation P I have written as it is. This is an application of domination law for us. Domination law. Now what is F? F naught or Q and negation P? Using identity law, F naught or P is nothing but P itself. F naught or P can be written as P only. So this is nothing but Q and negation P only using identity law. So which law did we apply here is using identity law I have obtained this. Q and negation P. What was our V dual? V dual was negation P and Q. So we are close to it now just by applying commutative law. I will be able to obtain that now. So negation P and Q by applying commutative law for us. Applying commutative law. By applying commutative law. So U dual is finally equal to, what is U dual we have obtained? Just mark the same thing. U dual is now logically equivalent to negation P and Q. So this is my expression 2. So what can we conclude from 1 and 2? U dual is logically equivalent to V dual. So that proves the principle of duality. So hence I'll just conclude here. Hence U dual is logically equivalent to V dual. U dual is logically equivalent to V dual, which proves the principle of duality. So these are the problems that I would like to work on. Laws of logic for you and the dual concept. Hope you have understood these problems. Thank you for watching.